Hi, welcome to this next edition of Science Class Notes. Today we're looking at half equations and redox titrations. Typical questions, very synoptic. Half equations you would have done in the redox topic in physical chemistry. Redox titrations are more to do with later on year 13, where you'd go over a topic called transition metals. So a mixture of both. Coming up, so good revision on both topics and overall calculations. Of course, titrations, that is to do with amount of substance. This question is broken up into two parts. I'm not going to really focus on this first question. However, like always, you can pause the video and have a go at the question, check the answers later on with the mark scheme. But really today I'm not concentrating on part A here of this question. I'm going to look at a green solution of X, which is thought to have 2+ ions. We're going to look at the half equations of that and the redox part. So let's go on from there. So here we go. So this part B is what we're going to concentrate on today in today's video today. So it's broken down into two questions, I and double I. Once again, we're not concentrating on here today, but if you feel free to stop and have a go at I here, it's worth 2 marks. Otherwise, let's move on to double I. That's what we're going to be focusing on today. Right, first of all, writing the half equations for this reaction, and then using the information from above, which is the numbers, of course, to calculate the concentration of iron, just 2+ ions in the original solution of X. So this question is worth a total of 5 marks. Overall, the whole question is 11 marks. So let's begin. Again, feel free to pause videos when you feel you don't need to. So the first half then is I'm going to look at writing the half equation, so the redox equation for this reaction. Let's have a look at the information they've given us. So write the equation between iron, 2+ ions, and manganate, 7+ ions. From your studies, you must realize and recall and remember, I guess, that when it comes to these manganate ions, it looks like that. I mean, you can refer that to the top part of the equation anyway. And what you've got to remember, memorize, and they haven't told you in this part of the question, is unless they tell you any different, this happens. Okay, the Mn goes to Mn2+. Now, the first thing to do is work out the oxidation state of Mn before the arrow. Best way to do it, I think, is work out the oxidation state of oxygen, which is -2 for each oxygen atom. Because I've got 4 of them, it's -8. Just like algebra, I guess, you're trying to solve for X here. Once you've done that, you work out that Mn here is +7. And they've said that in the question already for you anyway. Right, so what happens to Mn before the arrow to after the arrow? Well, looking at it, it's gained electrons. How many electrons it's gained? 5. So we add that on this side. If something loses electrons, we write it on the other side, which I'll show you later. Now we look at the oxygen. Let's get rid of the oxygen. And the only way we can get rid of oxygen is through the acid. And the acid was added right at the beginning to solution X. So the acid was present before you added the potassium MnO4. Okay, so there's the oxygen being formed from the acid. We'll come to the acid in just a minute. I've got 4 oxygens here, 1 here, therefore I need to write a big 4 here. Let's account for the acids now, H+ ions, because that's what an acid is. And how many do I need here? 8 moles of H+ ion. Is this equation, half equation, now balanced? Well, let's take a look. I've got 8 H's here, 8 here. I've got 1 mole of Mn here, 1 mole of Mn here, 4 O's here, 4 O's here. So the particles are all balanced. Now the charge on either side, well, all you do is add up all the charges. So 8 plus -5 plus -1 leaves you +2 overall before the arrow. And looking at the other side of the arrow, water's neutral, therefore no charge on that, 2+. So that balances. So we now know that this equation is fully balanced. Let's go to the next half equation here. Draw the arrow in. Now this was involving iron 2+ ions. So here we go. We start off iron 2+ ions. Again, you must be aware that that happens. Now, one quick trick here, and I use all the time, is, well, if electrons are on this side of the arrow for the first half equation, they must be on the other side of the arrow for the second half equation. And let's just check. Fe, 1 mole of Fe on before the arrow, 1 mole of Fe after the arrow. Total charge before the arrow is 2 plus, 3 plus minus 1, 2 plus after the arrow. So we know we have a balanced equation here. Right, now thing to do is add everything together. But before we add everything together, we must account for those electrons. I've got 5 available electrons that, I've got 5 electrons are needed for this reaction to occur. Therefore, the other half equation, the second equation we've written here, must supply 5 electrons. So we need to cross multiply the electrons. Now, this is pretty straightforward. I've got 1 mole of electrons made here. Here, I don't need to multiply anything. However, because there's a demand for 5 electrons in the first reaction, I must multiply everything in this second reaction by 5. Okay, so then I'll have 5 moles here, 5 moles here, and 5 moles here. Okay, now we can, while we're ready to add up everything under the line, H plus is 5 electrons plus MnO4 minus plus 5 Fe 2 plus ions. And then after the arrow, I've got Mn2 plus 4 H2O plus 5 Fe3 plus our 5 electrons. At this point, we can cancel electrons if we wish. There they are, off they pop. Then if we again look at the particles involved, I've got 8 H's here, 8 H's here. I've got 1 mole of Mn here, 1 mole of Mn here. I've got 4 moles of O here, 4 moles of O here. I've got 5 moles of Fe here, and I've got 5 moles of Fe here. That's balanced. Now let's look at the charges. 8 plus minus 1 plus 5 lots of 2 plus. If I add it all together, that should balance what's on this side. Now, we've got, if you check that for yourselves, you should have equal charge on either side. What you need to do then, and the most important bit from this for the next part of the question, is to do some calculating. Now, let's just have a quick look. I've got 8 moles here of acid, 1 mole of this to 5 moles of this, which makes 1 mole of this to 4 moles of water, 5 moles here. So that's the molar ratio, the stoichiometry, that's a balanced equation on this side. Right, let's move on from there to the next part of this question. This next part of the question then involved using numbers, if you recall. And here they are. Now, what I'm going to do is I'm going to decode the numbers for you. I'm just going to put a quick note up the top here, just to remind myself I've got a ratio of 1 to 5. Okay, that's very, very important, because if we look back at the stoichiometry, the balanced equation here, MnO4 minus, it's 1 mole of that to 5 moles of Fn2 plus. So let's take a look then. Right, first thing to do now, decoding questions is really, really important, because if you use this technique in the exam, it'll save you time, and 9 out of 10 times, I'm going to say, you're going to get the answer right, because you're getting rid of the words. The words can confuse the brain, especially in stressful times like exams. So thing to do is let's decode it. Let's break out the numbers and tell us what they mean. So in the exam, you can do this. This is your script. You can write what you like on it. So I want to say I've got a volume of 50 cm cubed. So we'll write the number 50 cm cubed here, just to remind me that it's a volume of X. Okay, just words. I've got 50 cm cubed of an acid here. So again, I've got a volume of acid, and that's equal to 50 cm cubed. Okay, so bringing out the numbers really helps out. Then the next number I've got, well, I've got here 250 cm cubed, and that's it's made up volume. So it's 250 cm cubed of this solution. Okay, so what happened was you reacted 2 chemicals together, and that comes up to 100 cm cubed. And what you've done, you've made it up to 250 by adding distilled water to it. Right, the next number we've got down here is 25. 25 what? 25 cm cubed. Let's write it next to this. 25 cm cubed is is the portion I've taken out from the 250. That's what it says here. From a volumetric flask, that's what we said. And that was titrated with a, oh, now we've got some numbers here. We've got a volume, let's write it over here. Sorry, we've got a concentration, I should say. Concentration of MnO4 minus, and that equals 0.0205 mole per dm cube. Right, okay, that's interesting. Right, let's read on. So we've got that, and then at the end point of the reaction, the volume of, again, the MnO4 minus solution added was this. So I've got a volume here, and that's a volume of MnO4 minus, which happens to equal to cm cubed, 18.70 cm cubed. Right, now just looking at this, I can see that the only thing I can possibly work out is the moles of something, and there's the moles of MnO4 minus. So let's go ahead, do that. MnO4 minus, okay, there we go. So let's go ahead, and to work out moles, I've got the concentration and I've got the volume. So here we go. So the 0.0205 times 18.70 times 10 to the minus 3 equals, into your calculator, remember you can pause these things if you wish. I get 3.83 times 10 to the minus 4 moles. Okay, that's of MnO4 minus. Now from there, what can I work out next? Well, because of our stoichiometry from before, 1 mole of MnO4 minus in ratio to 5 moles of the iron 2 plus. So the only thing I can work out next is the moles of, let's write it here, moles of Fe2 plus. And that's of course in the solution. So since we know it's a 1 to 5 ratio, therefore what we need to do is multiply, or good practice is 3.83 times 10 to the minus 4 divided by 1, because I've got 1 mole of that, multiplied by 4. It's always good practice to write things like that. That gives me a total answer of 1.92 times 10 to the power minus 3 moles, of course, of the iron 2 plus. Have you noticed in your calculator, the last number you calculate, the moles of MnO4 minus, you can leave that on your calculator practically, can't you? And you just multiply that number by 5. Little hint here for you guys. You don't really need to actually zero your calculator or anything like that. You can just go on from there. So let's see if that works for the second part. Now, that's great. I've got in the 25 cm cubed sample, I've got this this number of moles of Fe2 plus. But then that's come from, and the question was asking to calculate the number of moles in X. The X was 50 cm cubed right to start off with, right at the beginning. Now what I've got is I've got a fraction of, or a factor of 10 that I've taken out. And that was from the 25 cm cubed from the 250. Therefore, what I've got here is moles of Fe2 plus, but inside in the 250 cm cubed. That's what I need to find out, because that's where the moles came from before I did the titration. So I've got to account for the number of moles there. And that's really easy, because if I do 250 divided by 25, it's a factor of 10. So therefore, what we need to do is take 1.92 times 10 to the minus 3 multiplied by 10, and that will give you a factor of, let's just use 0.0192 moles. Now we're ready to move on from here, and just using the numbers again. I haven't done anything else. I'm not done here. The question asked to work out the calculate the concentration of Fe2 plus. That's what it was asking for in this reaction. So what we need to do then is work out the conc of Fe2 plus in X. Finally, we come here. We've got the number of moles in X already. if we look at the decoding, I've got a volume. I've got moles, I've got volume, I can work out concentration. Therefore, N is equal to CV. Always show the rearranged form as well. So C is equal to N over V. And we'll just pop the numbers in. Again, have you noticed I have not, or you have not, on your calculator, not once, have to zero your calculator, cancel any calculations, etc. And you can just carry the number forward in your calculator. Here we go again. So there's a number of moles. We divide that by 50 times 10 to the minus 3 because of the units, of course, decimeter cubed. Should have got an answer of 0.383 mole per dm cubed. Always write the units in if they don't have them. They expect you to do these things. Well, again, if you're not sure about what happened here, pause, go over the video again, repeat it again. But I'm going to show you the mark scheme, and I'll pause, and you can have a look at that as well. Okay, so this was for the first part, which we didn't go through. There's part BI, again, we didn't go through. This is part II, and the calculation underneath. Okay, guys, if you feel that was helpful, do pass this on to anyone else that needs this kind of help. Do recommend your friends to watch this, and in case they need any help with this. Thank you for watching. Please like and subscribe, of course.